Let us now see conditional probability axioms. Actually, these axioms are not new axioms, which means these axioms are same as the probability axioms. So I can say that conditional probability also satisfy all of those three axioms that we have already seen. Right? Now the first axiom is that non-negativity, which means that probability of any event, given that any event, like conditional on any event is greater than or equal to 0. Normalization, which means that summation of all the probabilities is 1, and additivity. So I will tell you about these three. So first let me just go to the non-negativity, which means that probability of any event given any other event is greater than or equal to 0. So this is the first axiom. Like actually axioms are there to not prove anything, but yeah, like since we already have the probability axioms, we can actually prove these axioms. Okay, so like I can say that these are the three things which conditional probability also satisfy, which means whatever the earlier probability rules were there, you can apply the same rules and given the event. Okay, so let's just prove it. Let's just prove that why this is greater than or equal to 0. See, this is nothing but probability of A intersection B upon probability of B. And obviously, this conditional probability is defined only when this is greater than 0, right? So now, since this is greater than or equal to 0, this is greater than 0 or something like that, then you will say that ultimately everything is positive, right? So ultimately, this is also greater than or equal to 0. And why these two are greater than 0 or greater than or equal to 0? Because of the probability definition, right? Because every probability is basically greater than or equal to 0. So that's why this whole quantity is greater than or equal to 0. Very, very easy proof. Now let's just see this normalization. This also has very easy proof. See, earlier what we had in the normalization, earlier we used to say that probability of sample space is 1. Now we want to say the same thing, but just that given some event B, it is also 1. That's what we want to prove. See, earlier we used to say that probability of A is greater than or equal to 0. We want to say the same thing, but now we want to say probability of A given B is greater than or equal to 0. Okay, so earlier whatever was the rule, we want to apply the same rule but given some event. Now let me just prove it. See, that's very, very easy proof. You can also prove it very easily. Intersection B upon probability of B. So sample space intersection B will be just probability of B upon probability of B, which is actually 1, right? Which is actually 1. So that's very easy proof. Now let's just go to the third point, which is additivity. So earlier, if you remember, in additivity, what we used to have, if A1 and A2 are disjoint event. So earlier, let me write earlier what we used to have, and now what we are going to prove, right? So basically, this is what we used to have earlier. Right, which means there was no given thing. So this is what we used to have earlier. Let me just write earlier. And now in the conditional probability we have this. So earlier we used to have this, now we want to prove this, where A1 and A2 are earlier were also disjoint, now they are also disjoint. So we want to prove it. Now let's just see if we can prove it, right? Okay, so I might use this earlier thing that we already have, so I might use it, but now let's just go to the next page and let's just prove it, right? Prove it. So proof. What is the LHS here? LHS, let me write the LHS, which is probability of A1 union A2 given B, which is same as probability of A1 union A2 intersection with B and upon probability of B, isn't it? Now can you just open this up? Can you just like apply the set theory rule? See, here the A1 and A2 are disjoint, so maybe I can make a Venn diagram. This is A1, this is A2, and now there could be some event B, which is, let's suppose, something like this, given B, right? Okay, this whole thing is a sample space. Now let's just see if you can simplify this. So here A1 union A2 intersection B. So I think A1 union A2 intersection with B. I think this portion and this portion will remain, right? So let me probably call this portion as small a, this portion as small b. So I can say that small a union small b will remain, right, upon probability of B. Probability of B is maybe I can say a small a union a small b union a small c, but anyway that's okay. But here this a and b are disjoint because this a1 and a2 are disjoint, so you can say this is probability of a plus probability of b because they are disjoint. And this is what we already know. If two events are disjoint, then earlier we have already seen that if two events are disjoint, then their union is same as, you can just convert that union to the plus, right? And now upon probability of b. So this is what LHS is saying. And what RHS is saying, a1 given b. So this a1 given b, right? So here if you just open this up, it will be probability of a1 intersection b upon probability of b, and this will be probability of a2 intersection b upon probability of b. So a1 intersection b is nothing but a small a, so this is nothing but probability of small a upon probability of small a upon probability of b. Similarly this is also probability of small b upon probability of b, which means that LHS and RHS both are same. This is what LHS have, this is what RHS have, right? So LHS and RHS both are same. So you can very easily prove it. Like there is no extra things that is required. If you want, you can do it little more formally, where you can say that okay, let me distribute this intersection over this union. Yeah, so I have this proof here. So here I'm distributing it first, and then since these two events are disjoint, so this intersection and this intersection, a1 intersection b, this one, a2 intersection b, this one, these two are disjoint, you can convert that to plus, and then you can separate it out, and then you are coming out with this particular expression, which is the RHS expression. Okay, I hope you understood. That's very easy proof, so you can also prove it. But now the takeaway is that whatever we had earlier as an axioms, those axioms are also satisfied here. So what you need to do, you can take any probability law, you can just do given b given b. So let me just show you that what do I mean by that. Okay. So maybe before that, I will just tell you one thing, and then I will tell you the difference or the similarity between the axioms of probability and the axioms of conditional probability. See here, what we had here, we were saying that it is greater than or equal to 0. Here just given b greater than or equal to 0. Here we were saying equal to 1, sample space equal to 1. Here I am saying given b. Here I was saying that a1 and a2 are disjoint. Then you can write like this here. Here just given b, right? So everything is satisfied here also. It is just that given b, or that's all. Like there is no other difference apart from given b, right? Okay. I want to talk more about the differences in the probability and the conditional probability. Not the differences, I can say the similarity, because everything is very much similar. But before that, let me just talk about something called as divide and conquer. Okay. So suppose, let's just consider a case where you have a sample space. And in this sample space, there is some event. You want to find out the probability of that event. Let's suppose that event name is B. And you want to find out the probability of B. Suppose this is the case. Now what you will do? I mean, you can find out if there is a way, but suppose there is not a direct way. Then you will say that, okay, instead of finding out probability of B, can I divide this B into smaller parts, maybe disjoint one, right? So can I divide this B into some smaller part? Let's suppose this part, let's suppose this event, this complete event is A1. Okay, this event is A2, this event is A3, this event is A4, this is A5, let's suppose. So can I say that probability of this B, I can write this B as just like that B is equal to B intersection A1, which means this portion, right? B intersection A2, which means this portion, intersection A3, this portion, this portion, this portion, right? So can I say something like this, B intersection A1, like probability of B intersection A1, union B intersection A2, union B intersection A3, which means I'm just rewriting this B, right? B intersection A5. I'm just rewriting this B, isn't it? So if I have some events, let's suppose A1 to A5, then can I not write like this? I can definitely write like this, right? I'm just rewriting this B. Now if I just ask you a very fundamental question, that how even you were able to write this B as like this? Okay, so let's just see like why we are able to write. See, suppose that here you have one sample space and here you have a event B and event B. Now let's just consider some events A1, A2, A3 to A5. Let's suppose, okay, or maybe A1, A2, A3, just 3 events. Maybe those events like looks like this. Suppose this is A1, this is A2, this is A3, this is A4, this is A5. Now can you write this B as intersection of this this B intersection A1 union B intersection A2 Can you write like this? Just think about it. What you will be getting if you write like this, B intersection A3, what you will be getting? See, there is no intersection at all, right? B intersection A1 will be 5, B intersection A2 will be 5, B intersection A3 will be 5. So can you write like this? Of course no, right? So you will say that we cannot write like this. So this is wrong. So you will say that we cannot write like this. Which means that there should be something such that you are able to write, right? I mean, there should be something about these age. And what is that something? Let's just see. What is that something? So basically you have one sample space and then you have some other events also. Like you have B and then some other events also. Now, I'm saying like you can write, but there should be some special property about all of these age. So this is B. Now the special property is that all the events A1 to till A5, like whatever the number of events you have, should be mutually exhaustive, which means that they should cover the complete sample space. Which means this A1 union A2 union till AN should be complete sample space, which is this phi. So if that is the case, then you are worry free. I mean, you don't have to worry anything. Which means this B will already be covered. Now, let's suppose this is A1, okay? Which means there is no intersection between A1 to A2, between A1 to B. Let's not worry about it. This is A2. But since all of these events A1 to AN covers this sample space, so they must be covering B somewhere, right? So let's suppose this is A3, this is A4, this is A5, this is A6, which is having nothing common. This is A7. Now, can you write B intersection A1 union B intersection A2 union B intersection A3 union B intersection A4 like that? Can you write like this till union B intersection A7? Just let me know. What do you think? The answer is yes. Because it may be phi, but B intersection A3, see, since it is mutually exhaustive, so this part must be covering in some age, this part must be covering in some age, this part must be covering in some age. And since you are writing all the age, then automatically all the parts are covering, right? So if these are mutually exhaustive means that all of these combinedly make the sample space, then you can definitely write like this, right? So to write this, you can say that we should have all the AIs as mutually exhaustive means they should be covering all the sample space. Okay, now you have this. Let me just go to the next page. Now you have this B, which can be written as a summation of some other events like A1, A2, A3, something like that, right? So this is, let's suppose, B. Now you may be having, let's suppose this is A1. Okay, let's suppose this is A1. Maybe A2 is also overlapping with A1. Maybe this is A2 or something like that, right? So what I want to convey, one last thing, is that even though you are able to write B as a union of all of these events, which means B intersection A1 union B intersection A2 union, something like this, right? Union, let's suppose B intersection A3. Let's suppose these are the three events. Although you are able to write like this, then if you just check this B intersection A1, which is this part, and B intersection A2 is actually this part, this complete part. So basically here these two events are not disjoint, right? These B intersection A1 and B intersection A2 are not disjoint here. So can you not write like this? No, I'm not saying that you cannot write like this. Even though A1 and A2 are not disjoint, I don't know if I'm confusing you, but see, what is the requirement to write like this? The requirement is that they should be mutually exhaustive. Disjoint is not a requirement, okay? Here, okay? So disjoint is not a requirement, but we want disjoint also. I will tell you why. Because if this A1 and A2 are not disjoint, then some portion may be covering in this B intersection A1, the same portion may be covering in this B intersection A2. But the set theory doesn't require me to be disjoint. Reason being is that set theory allows this equation even though these are not disjoint, right? This a1 a2 they doesn't need to be disjoint. It is not plus. It is not 1 plus 1 plus 1 equal to 2. It is not like that I'm double counting this portion or something like that. It is union, so it will always be counted once. It's not like that I'm double counting or something. So set theory doesn't say that that a1 a2 has to be disjoint, but the probability needs it. Why? Because if you take the probability of this event and they take the probability on the both side, which means you are rewriting it, then if these are disjoint, then you can easily able to write this as probability of B intersection A1 plus probability of B intersection A2 like this, right? If these are disjoint. So from here to here you need A1, A2, A3 disjoint, right? And if A1, A2, A3 are disjoint, then automatically B intersection A1, B intersection A2, B intersection A3 are disjoint. The reason is very simple. B intersection A1 is just some part of A1, right? Maybe this part of A1. If A1 itself is very different from A2, then some part from A1, some part from A2, some part from A3 is itself very different from or automatically basically disjoint, right? Some part from A1, some part from A2, some part from A3. It doesn't matter, right? If A1, A2, A3 are disjoint, then automatically B intersection A1, B intersection A2 and B intersection A3 are disjoint. So you can say that what we need finally is that we need them to be mutually exhaustive. We also need them to be mutually disjoint, right? Why exhaustive? So that I can write this be like this. Why mutually disjoint? Because I want to have the probability and then finally I want to have the plus symbol here. Okay, you don't need to remember this, you don't need to worry about it. Just remember one last thing is that if, now let me just write the rule, okay? If A1, A2, A3 till let me just take three events, A1, A2, A3 are making, that is called, in set theory you will study this, that is called partition, okay? Partition. In one word, that is called partition, making partition. Then actually partition means, let me just write the partition meaning also. Partition means A1, A2, A3 are mutually exhaustive second point is A1, A2, A3 are mutually disjoint. Right? These are the 2 points. Now, let me just write the rule. If A1, A2, A3 are making the partition, which means these are the 2 points which it is following, then for any event B, we have something like this. Probability of B equal to probability of B intersection A1 union B intersection A2 union B intersection A3, right? I hope you understood. Which is equal to probability of B intersection A1 plus probability of B intersection A2 plus probability of B intersection A3. Okay, I hope you understood. So basically the finally you can say that if A1, A2, A3 are making a partition, then you can rewrite this probability of B as a probability of small events. So that's actually very useful in probability theory. I will tell you the examples. Okay. See, in the random variable, what we will do, there's a part, later part, but I'm just telling you upfront that what we will do. Let's suppose we want to find out the probability of x equal to 2, but you don't have the marginalized probability. Actually, this is called the marginalized probability. But suppose you have the joint probability distributions. Then what you can do, you can basically just marginalize or just put y equal to k. Okay, which means you can say that for all possible values of k equal to 1 to n or whatever, which means that that if you want to find out the probability of x equal to 2, then you can just plug in the variable, the extra variable that you have. And since I will tell you in the random variable, since all the values makes the partition, okay, so y equal to 1, y equal to 2, these, and y equal to 3 till y equal to, I mean, all the values of all the possible values of any random variable makes the partition. Okay, every individual thing is one event, and these events are mutually exhaustive, combinedly mutually exhaustive and mutually disjoint also. So anyway, we just plug in some extra random variable, and then we find out the value. So this is one trick that we will play. I think earlier also we had some example. We wanted to, if you remember, there was one question where in the soccer game question, we want to find out the probability of goalkeeper, that you will be goalkeeper or not. In that case, what we did, you can introduce anything which is mutually exclusive and exhaustive, which is, I mean, you don't need to think that much. You can just, with the common sense, you can just introduce something. See, the goalkeeper could be with the Sam or with the Alex, right? So if you remember that particular example, so this is goalkeeper with Sam, which means comma means intersection, okay, comma and intersection are same. Goalkeeper and Sam plus goalkeeper and Alex. If these are the only two possibilities of the coach, you can do it. So if you find some events where you say that, okay, these are the only possibilities for that events, and in the tree diagram also, this is always mutually exhaustive, because the summation of any node, outgoing edges of any node will be just 1. If this is 0.5, this will be 0.5. If this is 0.3, this will be 0.7. So this summation is always 1, which means these events that go out from any node is always mutually exhaustive. Okay. So I hope you understood this. Little you might got understood that what we can do, you can find out the probability of any random event by breaking down into the probability of some other events. Basically, this is called marginal probability, and this is called joint probability. So basically, you can find out the marginal probability using the joint probability distribution. And this process is also called the marginalization. I mean, some people call it total probability law, but in machine learning, we call it marginalization. Okay. So actually, I remember one instance in machine learning class. So Chiru sir is one of the very popular professor in machine learning at ISC. So he used to say that, okay, let's just marginalize this probability distribution, which means that you have the joint probability distribution, and now you want to find out the individual probability distribution or the marginal probability distribution, and the whole process is called marginalization. Okay, cool. See here, this A1 to A6 are mutually exhaustive and disjoint. So if this is disjoint, exclusive means exclusive and disjoint both are same. Either I say mutually disjoint or mutually exclusive, both are same. Okay. So these are the disjoint events and also the mutually exhaustive events, which means covers the sample space. Then this B can be broken down into B intersection A1, B intersection A2, B intersection A3. This is B intersection A1, this is B intersection A2, this is B intersection A3, this is B intersection A4, B intersection A5, B intersection A6. So you can just break down this B into multiple parts. Okay. So this whole process, as I said, this is called marginalization. If you have three events, A1, A2, A3, then you can easily do this. And this is very easy to prove using Venn diagram. We just did it, right? So what we did using Venn diagram, this was B, this was A1, this was A2, this is A3. So this is A1, this is A2, this is A3. And what we did, we just said that, okay, this is B intersection A1, B intersection A2, B intersection A3, which means B can be written as B intersection A1, union, B intersection A2, union, B intersection A3, and then since these B intersection A1, B intersection A2, B intersection A3 are disjoint, that's why this union can be converted into plus. So that's how very easily we can prove it, right? We just did the proof. So this law is also called the total probability law. So you can call it total probability law. Although some people like to call it marginalization, and some people means that ISC professors. Okay. So but generally we call it total probability law. Cool. Now, we have already seen the examples of probability. Now, let me just, examples of probability and examples of conditional probability. Now, let me just tell you the similarities between these two. See, here also you have greater than or equal 0. Here also you have greater than or equal 0. The sample space is 1. You just say given B. You just say given B, the sample space is 1. Here, the additivity rule is saying that probability of A1 union A2 is probability of A1 plus A2. And here also we have already proved it that here also you just do the given B things. Okay, given B. Whatever rule that is there in the probability, you just follow the same rule. You just say given B. Given B means that you are reducing the sample space basically. That's all. But the rules will be same. Okay. So if the some rule is getting followed there, then it will get followed here also. It's not a problem in the reduced sample space. Cool. Now here earlier we had one rule which is basically saying probability of any event is number of events in a number of elements in A divided by total number of sample points in A. So that is also followed here, like A given B. Here it will be number of elements in A intersection B upon number of elements in B, right? Now inclusion exclusion principle says that you have this particular equation. Now you can do the given B things, and you can still have the same equation. We can easily prove these things. Okay, this inclusion exclusion principle, De Morgan's law, these things we can easily prove it, but that's not required. Let's just take it as words, which means you can do the given B. If you want to really prove it, you can do using the formula. How? Just open this using the formula, and what is that formula? This simple formula. See, this probability of A given B is probability of A intersection B upon probability of B. This simple formula, using this simple formula, you can just prove, you can just open up the left hand side and right hand side also. And using the Venn diagram and all, just try proving. If you want, you can just try proving this one and this one. Just try proving this. But for the normal probability laws, we have already proved it, right? So if that's the case, you can just do the given B. If that's the De Morgan law, you can just do the given B. Okay. So in the given B also everything is true. I hope you understood. Now let's just see more probability laws that we have already seen. See, the probability of A and probability of A complement will be 1. Here also given B, it is 1. Okay. The total probability laws that we have seen just now is basically the probability of B can be written as probability of B intersection A1 plus probability of B intersection A2, like that. Here also B given, let's suppose some event A, so given A. Everywhere you just write the given A. Now we will see this Bayes theorem later. Like we have already seen it, but yeah, we will see formally Bayes theorem later. But yeah, this is the theorem that we have here. Now you have the same thing here, which is given E also. So given E means B is already there. Then you can just write comma E or intersection E. Does not matter. So you can write the same formulas. You can write this A intersection B, the same formula, but everywhere given E, right? Everywhere given E. See. So there's a similarity between probability and the conditional probability. Now I hope you are very much familiar with the conditional probability. Okay. Now let's do 1 or 2 questions. Then we will jump to some questions which are specifically related to gate previous year questions. And those previous year questions we will be solving just using the very simple tree diagram. So this question says that if you have 3 bags, each containing 100 marbles. Okay. So there are 3 bags, each one is containing 100 marbles. And now they have given that bag 1 contains 75 red marbles and 25 blue marbles. Similarly, bag 2 contains 60 red, 40 blue. Similarly, bag 3 contains 45 and 55 blue and red and blue respectively, right? Now what they are saying, I choose one of the bags at random and pick a marble from the chosen bag. See, you need to identify the sequence of events. First, you are choosing the marble or you are choosing the bag. Just let me know with your common sense. Obviously, you will be choosing a bag first and then you will be choosing the marble, right? That's very natural sequence of order. So you will be choosing a bag, and there are 3 bags. So there are 3 possibilities here. You will be choosing a bag. Let's suppose that you have chosen bag 1 here, bag 2 here, and bag 3 here, right? Now what are the probabilities of choosing these bags? Let's just see the probability. They are saying that you pick a marble from the chosen bag. I choose one of the bags at random. So since you are choosing one of the bag at random, so I will say the probability of these 3 is 1 by 3, 1 by 3, 1 by 3, right? Now if you choose bag 1, what is the probability? Since you are choosing again randomly, what is the probability you choose red? See, they are asking that finally, they are asking the final probability that you get to choose red, which means irrespective of whatever bag you are choosing, finally what is the probability that you are choosing red? That's what they are asking. So let me just solve this question. So here you might get red or blue, right? So everywhere there are 2 possibilities, red or blue, red or blue, red or blue. Now the probabilities are different. Here the red probability is 0.75, here the red probability is 0.6, here the red probability is 0.45. And this probability I am not writing because otherwise the diagram will be little messy. But yeah, you got it right. This probability should be 0.25 because the summation should be 1. Now what they are saying that ultimately you want to find out what is the probability that you choose red. So red is here, red is here, red is here also. So you just sum up all of these probabilities, which means here this probability is 1 by 3 into 0.75. This probability is 1 by 3 into 0.6. This probability is 1 by 3 into 0.45. So the probability of being red is actually, since red is at 3 places, you can say 1 by 3 into 0.75 plus 1 by 3 into 0.6 plus 1 by 3 into 0.45. So this is the final probability and this is the answer. Now if they ask you a different question, let's suppose if they ask you what is the probability of red given that, or maybe okay, this let me just ask this question, what is the probability of probability of red given that you have chosen bag 2, then what is your answer? This is very much given in this question, right? The probability that you will be choosing red, given that you already know that you are with the bag 2, then the probability is 0.6. So this is already in the given question, which is 0.6. Now we will also see Bayes theorem, where we will just flip the question, which means instead of asking like this, we will be asking like this: bag 2 given that red, okay, which means that you already know that the chosen marble is red. What is the probability that it might have got chosen from the bag 2? That kind of question we will answer later. Actually, like these are the easy questions only, but we will answer little later. But for now, I just want to convey this tree diagram. I hope this tree diagram to clear to all of you, right? So how this tree diagram is working, you just have to identify the sequence of events. That first you are choosing bag and then you are choosing either red or blue marble, right? So you first choose bag and then you are going for red or blue marble. Okay, so that's what it is happening here. Now easily you can make a tree diagram, and based on the tree diagram you can definitely answer the questions which is question which is asked in the question. Okay, now let me move to the next question. So this question is saying, you enter a chess tournament where your probability of winning a game is 0.3 against half of the player, and let's just call them type 1, and 0.4 against the quarter half of the player, and 0.5 against the remaining half of the player, remaining quarter of the player. So let me just make you understand with one example. Suppose this is me, okay, suppose this is me, which is Sachin. Now I might be having two friends. Let's suppose one of them is Mohan, right? Another one is, let's suppose like any name, Suman. Okay, let's suppose these are the two friends that I have. Now what may so happen that this particular friend might be so weak in chess that I might say that the probability of winning me could be, let's suppose could be let's suppose 0.7. The probability of winning me, okay, against him maybe 0.7. And maybe it is also so weak, this particular player is also so weak, and then I say that probability of winning against this maybe 0.8 or something, right? So what I want to convey from this example, there are two friends that I have. One is me, there are two friends. I win against Mohan is the probability 0.7. I win against Suman is the probability 0.8. Which means that this summation need not to be 1, right? I mean, see, these are the individual probabilities that I have. You don't say that, okay, why this summation is not 1. Reason is very simple. When I'm talking to Mohan, Suman even does not even exist, right? Which means I'm only dealing with Mohan. So this is the probability that is telling me what is the probability of me winning against Mohan. What is the probability of me winning against Suman? So these are the two different probabilities. Even I can have multiple friends. Let's suppose there is one more friend that I have, and let's just call it call this friend maybe Abhinay. And then okay, sorry. And then if I just say that what is the let's suppose this player is so strong, okay, so if I just ask you that what is the probability of me winning, maybe it is very less, maybe let's suppose this is 0.1. okay, so actually these three probabilities, what I want to convey is that these three probabilities very much independent, right? That's what I wanted to convey here. So similarly here, what is given in the question is the independent, I mean the probabilities that I am winning against the type 1 player or type 2 player or type 3 player. So there are different type of players. Let's suppose this is me, and if I'm dealing with type 1 player, which are actually the population of type 1 player is too much, right? I think the half of the players are type 1 player, but yeah, that's okay. So if I play against this type 1 player, then I win is 0.3 probability. Similarly, if I play against type 2 player or type 3 player, so these are the three different probabilities that they have given. If I play against type 1 player, then I win is 0.4 probability. If I play against type 3 player, then I win is 0.5 probability, right? So these are the three probabilities that I have. I hope you understood. Now this summation need not to be 1. Reason is very simple. I hope you also understood the reason. Okay, now what they are asking is that you play a game against a randomly chosen opponent. Okay, see, you need to identify the sequence of events. First you are choosing the opponent, and then you are saying that okay, what is the probability winning, and then you are actually playing the game, which means either you are losing or you are winning, but that is after choosing the opponent. So since there are three type of opponents, see, this is not the tree diagram, this is just a visualization I wanted to give you, but yeah, this is not the tree diagram, but let's just make the tree diagram. So initially you will be choosing a player, maybe it is type 1, maybe it is type 2, maybe it is type 3. Let's suppose maybe it is type 1, maybe it is type 2, maybe it is type 3. So initially you are choosing a player. Now once you choose the player, what you will be doing, you will say that okay, once I choose the player, then I will be either winning or I will be losing, right? Either I win or I lose, I win or I lose. Now let's just see what are these probability of these edges. So what is the probability you choose the type 1 player? Since type 1 players are half of the players of the population, that is why 0.5 is the probability that player will be type 1. What is the probability that you choose type 2 player? Since type 2 players are the quarter half of the players, that's why 0.25 is the probability that you choose type 2 player. Similarly, type 3 is also quarter half of the players, that is why 0.25 is the quarter of the players, that is why 0.25 is the probability that you choose type 3 player. And once you choose any one of this player, either you win or lose. And these probabilities are given to me, which is you win, I think 0.3 probability, then it will be automatically 0.7. This is 0.4 probability, it will automatically be 0.6. This is 0.5, it will automatically be 0.5. Right? So that's how you make the tree diagram. Now they are asking what is the probability of winning, which means they are asking the probability of winning, and win is at 3 places. You need to add all of these 3 probabilities to finally get the probability of winning. Right? So let's just add all of these 3 probabilities. So probability of winning. Let me do one thing. Let me just copy this maybe, right? Now if you just ask me the probability of winning, then it will be 0.5 into 0.3, this node plus this node, which is 0.25 into 0.4 plus this node, which is 0.25 into 0.5, yeah, 0.25 into 0.5. And the final answer is, let me just see the answer here, 0.5 into 0.3, 0.25 into 0.4, 0.25 into 0.5, yeah, that's correct, which is 0.375. So the probability that you will be winning will be 0.375. That's how easily you can solve this question, right? Okay, now this is the solution that we have. Now let's just solve one more question, which is easy question, but let's just solve it. Now they're asking true or false. So these two equations are given. Let's suppose this is A, this is B. Now you just need to tell me whether this is true or this is false or something like that. Just do this as in homework, and then we will be solving this in the next video. So in the next video we will be just solving it. Okay.